Okay, I was just going to start by saying, well, thanks for being flexible for last week, by the way. Feeling a lot better. Literally spent probably 30 hours on the ground and then another 30 hours in a lot of pain trying to move around. So I feel pretty good today, and I'm sitting at my desk, and we're going to do this thing. I wanted to mention that, though, because I had fallen behind on grading a little bit. I did go ahead and grade project 1, and so those grades are up on Blackboard. I am going to hold off on posting solutions for a little bit because I'm working with some people on that still. Having said that, I think I'd like to only do one project. I have a second project, but since I'm having a hard time getting people to finish the first project, I don't think I'm going to dump a second one on everyone, especially given the circumstances. So if you're in the boat of one of those couple people who aren't really responding to my emails, I see they're in there, you're here, and so I'm going to take this opportunity to talk to you. If you're not responding to my emails, I don't really know what to do other than keep sending you emails and trying to help you and trying to get you material. So if you're one of those people who hasn't turned in project 1 and has been ignoring me, I'd like to give you another option, and it'd be nice to give you that option once you respond to some of my emails. I've sent a lot of emails out, and I'm just getting nothing in response from some people here. So I know we're having tough times here, but I don't know whether you're having a tough time, whether you don't have internet, whether you're just ignoring me, whatever it is. It'd be nice if you would please, and there's not just one person, so I'm talking to a number of people, and there's only 5 people on this thing right now, and I'm talking to more than one of you. So anyway, please try to respond to those emails. I'm trying really hard to help you, and it's getting a little bit frustrating not hearing anything in response. Having said that, can I answer some questions? Does anyone have any questions about homework or what's going on in class or pass, fail, or anything else you want to discuss before we get started here? All right. If not, we're going to get started. I put a few Maple codes in the Dropbox that we will look at throughout the course of this meeting. This is, in my opinion, a pretty important class because we've been building to this Fourier series stuff all semester. We did a bunch of linear algebra review, including inner products and projections that were sort of leading into this approximation of functions. And so here we are. And so this is where we left off at the last class. This is the last page we were on. And I sort of set up the idea, and I just want to remind you of it before we look at some examples. And again, we'll look at them on Maple as well. Please do stop me at any point here. So the idea is we have a periodic function. And so a periodic function means the function repeats itself. So think like sine or cosine, for example. That's piecewise continuous. It turns out that the Fourier series, which is given by this, is a good approximation to that piecewise continuous function f of x. And so at the bottom it says that we get a good approximation. Before we look at the bottom here, the idea is that the a0, the an, and the bn in each one of these cases is given by these 3 expressions. And so we've got an inner product here, and you can see we're doing the inner product with the function and the number 1, the periodic function and the number 1, the function we're trying to approximate and cosine of nx, and the function we're trying to approximate with sine of nx. And so we're essentially projecting sine and cosine, which are periodic functions, onto some piecewise continuous expression. And I mentioned like maybe we'd look at some YouTube videos. I thought maybe we'd look at actually doing this first and then talk about the application. So maybe we'll look at that maybe on Thursday. But you can see that what this ends up being is some integrals. And we spent the last couple class periods sort of reminding ourselves about the tools to handle these integrals, right? So we know how to do like, we can do integration by parts pretty quickly using tabular integration. We know that, let me just get out some of that information so I can show you. So we talked about like the tabular integration, that'll be helpful for that stuff. We talked about everything that's summarized on this page. Remember on page 11, I kind of summarized a lot of the things there that might be helpful, including things like, where's the page I'm looking for? The page that talks about like, even and odd functions, like what's an even and odd function, what happens when you differentiate them, what happens when you multiply them. And so all the stuff we've been looking at the last couple of days, right? When you've got an even or odd function on a symmetric interval, what happens? We're going to kind of use all that information when we're doing these integrals here. So I will try to keep that stuff handy, but you want to know where that stuff is as well. So like pages 7 through 13 or so. And the whole takeaway is this function that we're trying to approximate, this periodic thing f of x, can be approximated with the Fourier series. And you can see this is an infinite series, right? It goes to infinity. And so the more terms we add, the bigger the expression will be, and the better approximation that'll end up being as well. Okay, so we're going to look at some. Can I clarify anything about that? We're going to look at least like 3 examples of that today, as well as their corresponding maple deal. Any thoughts about that at all? I should also maybe remind you that we've got homework due on Thursday. So homework 5, the next homework set, is due this Thursday. And we've already finished covering that material. And then homework 6 is on the material that we're covering now, which is due in 2 Thursdays from now. So kind of thinking about assignments throughout the rest of the semester, your grade, what's left are, I believe, probably 3 homework assignments. So homeworks 5, 6, and then there'll be at least a 7. And then we'll do a take-home final during that last week of school. And so there's those, I believe, will be the last assignments that are out there. Okay. Again, please interrupt me at any time. So what I've done on this page is I've actually just I've written out the Fourier series already. I've actually done and typed out all the work here. And I want to kind of go through it and annotate it and answer any questions that you have about it. And then the next one, we're going to do completely from scratch, right? So there's not much written on the next page. And so the question here says, find the Fourier coefficients and the Fourier series for the periodic extension of this square wave. And we'll define the function to be its periodic extension of period 2 pi. So what that means is, so this function says if we're between 0 and pi, we're at the number 1. And if we're between minus pi and 0, we're at -1. And so that's this part of the graph right here. So it's defining the part between minus pi and pi, right? Here's the part down at -1. Here's the part up at +1. And then when we're going to see this word a number of times throughout the rest of the course, this word periodic extension. It just means copy one period and extend it in both directions. And so if we copied that period that I boxed in there and we just pasted it to the right, it would be this piece right here, right? And if we pasted it to the left, it'd be over here. And then it keeps going, right? There'd be another one down here and up here. There'd be another one up here and down here, and it kind of just copies both directions. And so the way these things are often defined is you define one period, which I boxed in red, and then the periodic extension is just copying that period and pasting it repeatedly. Is that okay? Okay, and so again, what I've boxed in here is one period, and then what's being shown is the periodic extension. So we're gonna do a bunch of integrals involving f of x, right? So we need to define the Fourier coefficients, and we define those using these things here, right? So we do the inner product of the function with 1, the function with cosine of nx, the function with sine of nx. And so that's what's going on down here, right? We're finding a0, an, and bn. And in order to do these integrals, it's helpful to know whether or not, whether the function is even or odd or neither. And so if we're looking at this function, one of the things we talked about in the last couple classes is certain functions have certain types of symmetry. So thoughts about what type of function this is? Is it even or is it odd, or does it have some type of symmetry? Anyone?
Looks odd.
It looks odd because? Why'd you think that?
Not sure how you worded it last time, but if you reflect over the x-axis and then the y-axis, it looks like it would line up.
Yeah, so if you do both the reflections, it looks like it lines up, which means that it has symmetry with respect to the origin, which is what Nick just says. And so the way I thought about it last time is if you turn it upside down, it looks the same, as one way to sort of say that. And so this one, f of x has symmetry with respect to the origin. And so if it has symmetry with respect to the origin, what we said a couple classes ago is that it's an odd function. And so we know a bunch of things about integrals of odd functions. And I'll also remind you that if you do an odd times an odd, you get an even. And if you do an odd times an even, you get an odd. And so keep that in mind, because that's how you simplify these integrals, and you don't have to really think about them too much, because if you know you have an odd function or an even function, you know certain things about their integral. So I'm not going to write down all the properties, but what we had said specifically was on page 8, right? If you integrate an odd function around the origin, it just ends up being 0. And if you integrate an even function around the origin, it's just twice what you get around one side. And so that's how these integrals were calculated. And so there's not work shown there for these integrals, because we don't need to show work, because we just know what the answers are based on what I just said. So I've just lost what I was looking at here. Just misplaced something, sorry. Okay, I got it. So do people see what I'm saying? Like, in other words, this is A0. And again, I'm just doing this definition, right? I'm doing the inner product of the function with the number 1. And so the inner product of the function with the number 1 is just the inner product is just the function integrated from minus pi to pi. And why do we know it's 0 without doing any work?
Because the function's odd, we know that the area on the right will be the same as the negative area on the left, so they have to cancel out.
Awesome. Right, just look at the picture. Like, if we integrate this picture between minus pi and pi, the area over here that I'm highlighting is negative, and it's the same area as right here, except this is the positive version. So those two things cancel each other out, just like Zach said. And so this is just 0 without even doing any work. Now we could integrate this, like we could break this up into, minus pi to 0 would be -1, 0 to pi would be 1, but we'd end up getting 0 anyway. And so it's just kind of like a shortcut to avoid doing work, basically. And we do a similar thing on this one too. I'm not showing any work here because f of x is odd, we just said. We had said previously that cosine is always even. And so what we have here is we have f of x times cosine of nx, which is an odd times an even, which we just said a second ago is going to be odd. And so again, we're integrating an odd around the origin, and we know that's going to be 0. So again, we don't have to do any work on either of those two integrals, because we know some tricks about integration and even odd functions. The third one requires a little bit of work, but let me just see if there's questions about that. That so far. These first two seem okay, and that's the way these all work. I'll show you how to use Maple eventually, but if you're doing these by hand, you can usually just do some shortcuts like this. Okay, what's going on in the last one? So we're doing the inner product. Let me show you the formula again. We're doing the inner product of the function with sine of nx, and so we're multiplying those two things from minus pi to pi. That's literally exactly what it says on the previous page here. And the first step here is I've rewritten this as 2 times the integral from 0 to pi. Why did I do that? What's going on with that one? when we do f of x times sine, what does that end up being? It's going to be an odd times an odd, which is even. And we know that when we integrate an even function, you get 2 times half the integral. Right? And so the integral of minus pi to pi of an even is 2 times half of it. And so that's what's going on in this one, right? So you, instead of going from minus pi to pi, you just go from 0 to pi, but you're multiplying it by 2. Let me zoom out a tad here. Thoughts about that? Just going to join on my other computer here so I can see what my screen looks like. Okay. Okay, and so then we're integrating this like sine of nx from 0 to pi, and we know that when we integrate sine, it just becomes minus cosine, but then you divide by n, right? So here's how you integrate that. And then we're evaluating it from 0 to pi, and it becomes this. And so I don't know if that makes sense or not. Let me maybe show the details from that. Where do I have space to do that? Maybe I'll just do this right here. So when you do... I'm going to evaluate this from 0 to pi. So it's going to be 2 over pi minus cosine of n pi over n minus cosine of 0 over n. Right? Cosine of 0 is always 1. And so this piece right here, including the minus sign, is just going to be, you're going to get 1 over n here. And so the minus signs make a plus. So it becomes plus 1 over n. And then the other piece, cosine of n pi over n, when we think about that, let's think about different values of n. Right? So n is an integer, and eventually it's going to be part of this series where you're plugging in n into this for successive n's. And so let's see what happens when you plug in n equals 1, and then n equals 2, or n equals 3. Let's see if we can come up with some pattern. So when you plug n equals 1 into this, you get cosine of pi. Cosine of pi is negative 1. And so this ends up being minus 1 over 1. When you plug a 2 in, you get cosine of 2 pi, which is 1. And so this ends up being minus 1/2. When you plug a 3 into n, you get cosine of 3n. I'm sorry, cosine of 3 pi, which is negative 1 again. And so you'll get this again, right? And so you can see, I don't know if you can see it, but there's a pattern here, right? So the number on the bottom is going up every time. And then the inside negative part switches every time. And so overall, this ends up being 1 over n will make the bottom go up, right? And then you make the sign switch by doing this, minus 1 to the n plus 1. Right? Because when n is an odd number, it'll raise it to an even power and make it go away. And when n is an even power, the opposite happens. Thoughts about that? And so that's how you got like this inside expression right here. Right, the 2 over n pi part, the n comes from the denominator, and then the minus 1 parts come from these two things. Anyway, you don't have to like simplify it like that. I just wanted to simplify it a little bit and show you how you can sort of write something a little more succinctly. But when you put it all together, this ends up being the full expression. And so let me walk you through that part. So back on the last page here, we're doing a0 plus the sum of an cosine nx, bn sine nx. And we just calculated the a and the b's, right? And so A0 was 0, so that term doesn't exist. And then AN was also 0. And so you can see that both these terms went away. Like this isn't there, and this one's also not there. So we only are left with the Bn sine of nx. And that's exactly what is right here. This is the sum n equals 1 to infinity. It's like 0 plus... Oops, sorry. I meant to have just the 0 out here. That's our an plus sum an cosine nx bn sine nx. Let's make this one a0. These two just ended up being 0. And so you ended up with bn sine of nx. So here's the bn and sine of nx. It's just maybe to be clear, this entire thing that I'm circling right here is just the bn coefficient. Can I answer a question about that? I think there's kind of one glaring question here, but I'm not even sure if people are listening to me, so I'm gonna maybe see if someone has something they want to say. I guess one thing I was wondering if people were wondering is, how did this thing become this thing? It should be the same thing, and it looks different. Thoughts about that? I'm expecting someone to ask that, so I'm not sure if people are following along or not. Let me just do that right here in case people decide to look at this later. So the 2 over n pi is the same, right? But this inside part changed. And so let's start with the original thing that was there, which is this. And I'll manipulate this and show you how it can become what's written right there. So what happened was this n plus 1 coefficient was split up. And so it became minus 1 to the n times minus 1 to the 1. Right? It's like bases, different powers, and so you'd add the powers and get that. And the reason for doing that is because now you can factor out a negative 1. Like there's a negative 1 in both spots. And so you can factor out the negative 1. And when you factor out the negative 1, you'll have minus 1 to the n. And then this becomes a plus 1. And so this is what's inside the second part. And the negative sign is this one. So anywho, I hope that makes some sense. Eventually, let me just maybe remind myself what it says in the homework. I think for the most part in the homework, you can use Maple to do these things. And so maybe doing these by hand isn't super important. I'm trying to see here, though. I think generally speaking, using Maple is okay. Anyway, questions about this one? We're going to do a couple by hand before we switch over to Maple. Anything there? Okay. Please stop me. If you're confused, I'd be happy to reiterate stuff. I'd rather like spend the period going back over something we've already covered than me just talking to myself. So please let me know if that would be helpful. Okay. So let's see here. I've lost my screen. Here it is. Okay. Let's find the Fourier series of the. Do I want to do this now? Do I want to show you Maple? Maybe I'll switch over to Maple real quick. just to show you this. I'm not suggesting you do this, so don't open Maple yet. I'll give you a chance to play with Maple in a second here. Let me just sort of show you the last problem we just did in Maple. Actually, no, I'm not going to do that. I remember why I'm not doing that now. Sorry. Let's look at the next one, and then we'll switch over to Maple. I just want to focus on sort of the procedural part first before we get into some of the more nitty-gritty stuff, which is what Maple will help with. Sorry about that. All right, let's do this one. So let's find the Fourier series of the periodic extension of the absolute value from minus pi to pi. So let's start by graphing what that looks like. So I'm going to make a graph of the absolute value between minus pi and pi. So absolute value just looks like a V, right? And so it does this. So that's the absolute value between minus pi and pi. And then the periodic extension of that would just be copying that and like copying what's between my hands and then pasting it over here and just keep pasting it forever, right? So it's just going to be like this sawtooth kind of looking thing. Sometimes this is called a sawtooth. Right, and so the first one will go between minus pi and pi. The next one is another 2 pi, so that'll go to 3 pi. This one over here goes to minus 3 pi, and it would just keep going in both directions. Okay, so that's a periodic extension. But again, notice how it's defined. It just tells you like one period, and then you just copy it. The periodic extension means you copy it. Okay. Is this even or odd?
Looks even.
This is an even function. And when Zach says it looks even, he means it has symmetry with respect to the y-axis. Right? If you folded it like a book, the two sides would line up with each other. So that's relevant again for the integrals. If we want to do the integrals, then it helps to know that we have f of x is even. And so let's find the coefficients. And so we'll do those integrals. So the first one tells us we should do the inner product of the function with the number 1 over 2 pi out front. And so let's do that. And so this is going to be a0. It's 1 over 2 pi times the integral from minus pi to pi of f of x times 1. So it's just f of x. And we know f of x is even, we just said. And so we know that when we integrate an even function around the origin, we just get twice half of it, right? So it's going to be this. All right, so I've switched the integration, but I've multiplied by 2. Maybe I should make this red as well. And then, so that's helpful because if we're just looking at this half of it, this is just, let me just maybe mark off what we're looking at. We're looking at the piece between my pens right now. And this piece right here is just the line y equals x. All right, like this is y equals x, and this one would be y equals minus x. So another way to do this would just be to break the integral into 2 pieces, integrate minus x from minus pi to 0, integrate x from 0 to pi, and you'll eventually get the answer too. This is just, again, it's kind of like a shortcut. And so we're going to integrate x dx. And the reason we do that is because our function equals x from 0 to pi. And that becomes a very easy thing to do, right? Just it's a power rule thing. Add 1, divide by, or add 1 to the power, divide by the power, etc. And so this is going to end up being, so the 2's cancel here, and we'll just get 1 over pi x squared over 2 from 0 to pi. And you can see that that's going to be pi over 2. So last time we got a 0 value for the a0 coefficient. Now we have a value of pi over 2. Just going to kind of pause after these things, assuming people are writing stuff, let you catch up, see if you have a question. I think this is maybe a little blurry. Can I clarify anything about that right now? All right, so let's find the next coefficient. So let's look at Bn. So Bn tells us we want to do the inner product. Oops, wrong page. Bn is we want to, or An, excuse me, we want to do the inner product of the function with cosine nx. And we know that cosine is even. And so when we do An, maybe let me do another color here so it stands out. So this is what the page I just put up there says. So we want to do the function times cosine nx dx. And what we got here is we have an even times an even, which we know is another even. And so again, instead of trying to, because f of x is hard to write down because it's minus x on one of the intervals and x on another part. And so it's helpful just to focus on one of the pieces, and then you can write down something for the function. Right? In other words, this will become 2 over pi. I should try to do that in red so you can see what changes. 2 over pi. And then again, we're going to integrate, but instead of minus pi to pi, we're going to cut the interval in half and then define the function on there. All right, so again, this becomes is that okay? How do we do this? How do we do the integral x cosine x nx, I mean?
Tabular?
Yeah, we use tabular integration. Thank you. And so I'm just going to do that real quick here. I think I've got the room. So I'm just going to slide it over here. One of the questions in the homework that's due on Thursday, I think, is to use tabular integration. So this is where you make a table with f prime, you alternate plus and minus, and then you have the integral of g. And so the thing you're taking the derivative of is a thing that will eventually become 0. So it's going to be x, 1, 0. Right? So you differentiate the x until you get down to 0, and then you alternate pluses and minuses, and then you integrate the other thing. So you start with cosine of nx, integrate for sine of nx over n. It's supposed to be an n, sorry. And then integrate that for minus cosine of nx over n squared. And then you draw a line from this down to this, and those two things multiply together. This down to this, those two things multiply together, and you separate them with the pluses and the minuses. So, so using that, we can do this integral now. It's just going to be, plus those two things minus those two things plus 0. And so this becomes 2 over pi times what I just said. So we have plus x sine nx over n. And then I got confused for a second. It's going to be double negative, so it's going to be minus a minus, and so I'm going to put a plus. It's going to be plus cosine nx over n squared. And we want to evaluate that from 0 to pi. And when we plug in 0 to pi, we get this. 2 over pi. So when you plug in a pi, sine becomes 0, right? So I'm not going to write that term down. So it's just going to be the cosine of n pi over n squared. And then when you plug in a 0, you also get 0 here. And so you just get a 1 on that one. And so it's going to be 1 minus 1, excuse me, over n squared. Sorry about that. Everyone's got a different looking screen, Matt. So I'm trying to, like I said, I've got a second monitor open to try to keep an eye on what mine looks like. But if I slide off the screen, do let me know. If I slide up your screen, I should say. So again, when you plug in pi into sine or you plug in 0 into sine, this just goes away. And so these two terms are just what you get when you plug those things into cosine. And then what we had seen on the last page is when n is an odd number, cosine is -1, and when it's an even number, it's +1. And so you can then write this as 2 over pi times -1 to the n minus 1 over n squared. So cosine of n pi becomes this. Again, kind of doing the thing that we did in the last page, which is plugging in successive n's into cosine and thinking about what happens there. And so we now have 2 of the coefficients. I'm just going to pause here and see if that seems okay. All right. And so then the last coefficient, bn, we do the inner product of the function with sine of nx. And so let's do that. So bn is going to be 1 over pi. Is it 1 over pi or -1? Let me double check here. 1 over pi times the integral of minus pi to pi of our function times sine of nx. And here we have an even times an odd, and we know that's going to be an odd. And so we're integrating an odd function around the origin. And so we don't have to do any work here, right? You should always just check this, see if you can do a shortcut. That's going to be 0 because we're integrating an odd function around the origin. This says odd. And so two of the coefficients, one of the coefficients ends up being 0 in this case. And so our final answer here, our Fourier series, is this right here. And oftentimes you can see, let me just maybe show you the notation before I write this down. The little f of x is the function we're approximating. And then oftentimes we represent the Fourier series with a capital F of x. And I guess we haven't actually defined that yet. I guess it's on the next page now that I think about it, or 2 pages from now. So I'll say this again in a minute here, but the little f of x is the period that we're approximating with period 2 pi, the function we're approximating. And then capital F of x we call the Fourier series for little f of x. So we'll define that more in a second. But anyway, that's why I'm writing a capital F of x here. So that equals pi over 2. That was our a0 term, plus our infinite sum of bn cosine nx. And bn is the thing that we just wrote down right here. And so that's going to be 2 times -1 to the n minus 1 over pi n squared cosine of nx. So this one is our bn. And there's no an because an ended up being 0. I'm sorry, that is our an. We didn't have a bn, it was 0. thoughts about that one?
I said a quick question.
Yep.
So the cosine nx on the end of it, is that there from the previous page?
Yeah, so the original formula here is this, where you calculate a0, an, and bn, and those themselves have sine of nx and cosine nx in them, right? But then once you find those, you multiply them by cosine of nx, sine nx sort of again.
Oh, okay.
See that?
And the bn ended up being 0, so that's why. Okay, yep.
Correct. Yep.
Okay.
Yeah, that's kind of an important part, right? Like this cosine of nx is different than this cosine of nx. You're using them. You use cosine of nx to find an, but then you also multiply it by there after you find it.
Right. So that's like right there on the bottom right. That cosine of nx is what you tagged on after it. So that's that one from the theorem.
Yeah, that's right.
Yeah.
This cosine of nx is from the theorem, exactly.
Okay, cool.
Other clarificational things? Okay. Okay, cool. I'm gonna do one more. This took me a little longer than I thought it might, but that's okay. I think we're in good shape. I think if we do these three, usually in class, when I run this in class, I have people work in groups on this thing. I'm just kind of feeling like maybe people aren't interested in doing that, but so I'm just gonna go ahead and do it. If you are interested in sort of giving this one a go, maybe go ahead and try it. Maybe just mute me or start it yourself if you want. If you want to watch me do it, that's fine too. So we're going to do again. We're going to do a Fourier series approximation of this periodic function, which kind of looks weird. And so let's draw a picture. So again, we're going between minus pi and pi again. And so that's going to be our first period. But this tells us that, and I didn't really draw a symmetric thing, unfortunately, but you can imagine that that's spaced evenly. So this tells us that to the left of the origin, it's just at 0. And so this graph is just like right here at 0 for negative values. And then it acts like the line pi minus x on the positive version. And so the line pi minus x has a y-intercept of pi, and then a slope of -1. And so that looks like this. So that's what f of x looks like. That's one period of f of x, I should say. And then the periodic extension of that would be copying and pasting that. So like if we copy and pasted it, it would look like this. That should be a straight line. And again, you could just keep copying and pasting it, and it just go on forever. But one, and it's interesting because these two signs sort of align with each other, right? They sort of line up right there. But the period that we're dealing with is these two things between my pens. Is that all right, that first part? This is kind of important because when you start to do the integrals, if you're doing something between 0 and pi, you use this function, right? And if you're doing something from minus pi to 0, you use this one. So kind of having an idea what it looks like can be helpful sometimes. Okay, I'm going to keep going if there aren't questions. So I'm going to calculate the coefficients. So I'm going to write down a0, an, and bn for all these things. And notice that, just notice that a0 is not part of the sum, right? When you look at the final answer, a0 is what's not in the sum. That's why it doesn't have an n down there. It's just like a constant. But these two things, an and bn, are going to have an n in the answer. And that's why they're part of the sum, because they're going to be sort of contributing to that sum every time you add another term. Anyway, I just thought I'd mention that. So anyway, let's calculate a0. So a0 is 1 over 2 pi, and then we do the function multiplied times 1. So it's going to be minus pi to pi of just the function. And again, this, I remember why this is a little bit different. So we don't have any types of symmetry, right? Maybe I should mention that. No symmetry. And so that means it's not even nor odd. So we may not be able to do many tricks on this one. I kind of forgot that was the case with this one, right? Does everyone see that? It's kind of important. We won't be able to do any tricks because it doesn't have any symmetry. If we fold it like this, it won't line up. If we turned it upside down, it would be different. And so if we want to integrate this from minus pi to pi, what we do is we realize, well, this piece is just 0. And so it doesn't, the area under the curve right here is nothing. And so we should just focus on the part that has area. And so let's just go from 0 to pi. And from 0 to pi, the function equals pi minus x. So there's no tricks there. It's just like thinking about what the function looks like, right? And this becomes a very easy integral to do. I won't bore you with the details. It ends up being pi over 4 when you do the power rule and all that kind of stuff, or the anti-power rule. What is that called? I always call it the anti-power rule, but I think I just made that up. Any calc tutors call that something different? I like the anti-power rule. Stick with it. Okay, and then the next part for AN, you integrate the function times cosine. And again, the function to the left of the integral is just 0, so you can just ignore that piece of it and just go from 0 to pi. And from 0 to pi, the function is pi minus x. So let me maybe add this in here. And you would use tabular integration on this one. I'm going to sort of spare you the details there and maybe just cut to the answer. This may be a good one to check your understanding of tabular integration. When you do tabular integration on this, you will end up with the following. 1 over n squared pi times n pi sine nx minus cosine nx plus xn sine of nx from 0 to pi. And again, I'm just going to kind of cut to the chase here. When you simplify that down, you'll get that. And we know that cosine of n pi is minus 1 to the n. So this could be written as 1 minus 1 to the n over n squared pi. I know I'm not showing details here. Hopefully you trust me, or you're able to check your work later if you want to. And either one of these is a perfectly fine thing to use, by the way. I'll just box both those in. You don't have to rewrite cosine of n pi as minus 1 to the n. That's just a nice thing that gets trig out of there, right? And you can see a little bit more clearly what's going on when you do that. But not necessary. You can program it into Maple or anything else using the cosine just fine. Just going to stop there for one moment here. Let's see if there are questions about that piece. Before looking at the last piece. Okay, the last coefficient then is the Bn. And the Bn, oops, I'm off the page. Maybe I'm almost off the page. For the Bn, you do 1 over pi, and then you integrate from minus pi to pi the function times sine of nx. And again, we don't have any even odd thing going on here, so we just got to do it with brute force and a little bit of thought. It's not really that hard because it's 0 on half the interval here, right? So anyway, this is going to end up being, again, just ignore the left-hand piece and just go from 0 to pi. We would again use tabular integration on this piece. And I'm just going to kind of cut to the chase here in the interest of time. I trust that you can do this. But I will try to write down some of the details in case you wanted to check your work when you're doing this or it comes up later or something. So this is what tabular integration would get you from 0 to pi. And then when you actually evaluate the bounds, it just ends up being n pi inside there, interestingly enough. And that actually simplifies down to just 1 over n. So that bn simplifies considerably when you do that. I just noticed too, like if the bottom of your screen's getting cut off, it might be because your cursor is like over the bottom of the screen. Like if you put your cursor in the middle of the video page, then the bottom goes away and you get a little more view there. So if that's going on with you, just might want to check that. And so we got our A0, AN, BN. I saw your question, Matt. It says, is that x times n or x subscript n? This is x times n, this one here, I'm assuming. They're all x times n. So they happen from like when you do the integration, you end up multiplying x times n. Other questions or thoughts? And so this is the first one where we got something for all three pieces, right? We got a value for A0, AN, and BN. And so there's something going on there. And notice this is also the first one that didn't have any types of symmetry. So there's something to do with symmetry and which terms you get, which we'll see on the next page. But maybe before we write that down, let's finish this one off and write our final answer. So our final Fourier series is going to be our biggest one yet because we got a bunch of non-zero coefficients. So the A0 coefficient was pi over 4. And then we have the sum, the infinite sum of our other coefficients, which ends up being this. And so this is like our A0. This one is our AN. This one is our BN. Thoughts on either of those three examples? This one in particular, but any of the three? And if you are caught writing things down, you should go ahead and open up Maple. We're going to switch over to Maple in just a second here. Anything there? Just box this final answer in here. There's a lot going on this page. Okay. So we will switch over to Maple in just a second, but let me just drive home what I just said in words. I had just said this in words, but it's written on the next page. So before we switch to Maple really quick here, what we just saw was if you're trying to approximate an odd function, so if you have an odd function you're approximating, then you're only going to end up with the sign terms in your answer, right? So we saw that in the first example, right? In our first example, 2 of the terms went away, and we only had the sign term because we had an odd function. And then our second example was the opposite, right? We had an even function. This one was even, and we only ended up with the a terms, right? In other words, the cosine. We didn't have a sine. And so if we're approximating an odd function, we'll only get the sine terms, and sine is odd. And if we're approximating an even function, we only get the cosine terms, and cosine is even. Okay, so if you're approximating an even, you only need the even function. And if you're approximating an odd, you only need the odd function. That should make sense. And the third thing we saw on the last page is if it's neither of those two things, you get all of them, right? So this example here wasn't even or odd, and our answer had both sines and cosines in the final answer. Right, so I should have added that in text here, but you should write this down. If you have no symmetry, this implies you get both sine and cosine. And it turns out that what we're doing is a projection, right? So we're actually projecting these orthogonal bases, right? So the functions 1, sine, and cosine that we're using in the formula are orthogonal, and we're projecting them onto these functions, which allows us to approximate them with these functions. And so I think what I'll do is I will start next class by finishing this convergence thing. So I'm going to switch over to Maple right now, and we'll talk about the rest of this page on Thursday. But let's look at a couple of the ones in class, from class that we just did in Maple. And so I'm going to present a couple things. You're welcome to open Maple yourself if you want, but you might just want to see me walk you through this for a quick second here. And maybe I should start by saying, is everyone able to see that okay, or should I zoom in, make the text bigger, or anything? Is that visible for everyone? Or maybe the better question is, can someone tell me if there's something difficult about seeing this, and I can try to make it bigger or something?
Looks good to me.
Okay, so there's two files in there, Fourier series A and Fourier series B. The A is approximating the square wave. And so you can see I'm defining the function we're approximating. It equals -1 when we're negative and +1 when we're positive. And so you get the square wave kind of thing. Let me just go ahead and plot the square wave. Okay, so there's the square wave plotted just like we just did there. I think someone just asked a question, maybe. I don't see anything. So when I share my screen, it creates 2 versions of myself, I think, and there's actually 3 versions of myself in here right now because I opened myself up too. So you should find the person in here who's sharing their screen and then pin that screen. Let me know when you're with us, Nick. It's a view of my Maple screen. So if you click like the people in the upper right hand corner, it shows everyone who's in here, and it looks like there's 3 versions of myself, and one of them says presentation. Okay, got it, good. Okay, so here I am defining the square wave. And here is the Fourier series, and so this is what we came up with as our final answer on the first page. Right, this is exactly what we had. It only has sine in there because we've got an odd function. And what I had done in here a second ago is I plotted, let's go ahead and plot capital F. You can see I'm typing in capital F. Let's plot the first 3 terms of capital F. And so when you put a 3 in here, like I'm highlighting, what that does is it makes n 3. And so it's going to sum from k equals 1 to 3. And so it's going to do 3 terms of the sine term. And so let's see what that looks like. Crud. Oops, I forgot to put a comma in here. Oh, there's a comma. No, I forgot to do that. That's what I needed. And so you can see with 3 terms in there, it's like it's not a great approximation, but you can see it's generally following the shape of the square function, right? Like the ones down here are mostly at -1, although it's oscillating around, and the ones up here are also by +1, but it's oscillating around. And the idea is the more terms you add, the better the approximation gets. So I'm gonna, instead of looking at 3 terms, let's plot the first 10 terms. I'm putting a 10 into the infinite sum. Well, you see it gets a lot better, right? And let me just go ahead and get rid of the other one so it's out of the way. You can see it's closer. And the more terms you add, the better it's gonna get, right? Let's add 30 terms. Really starting to hone in on those 2 lines that we're trying to approximate. Right? If you add 100 terms, it might take a minute to calculate, but it'll look really good, right? That's getting really good. If you add 1,000 terms, that might not run in enough time. Man, that actually went pretty quick. 1,000 terms gets real close, right? And so the next part down is just plotting a bunch of different approximations, right? So it's plotting the square function, and then the approximation with 10 terms, 50 terms, 100 terms, 500 terms, and you can see each successive approximation gets closer and closer and closer to the thing we're trying to approximate, right? You could kind of, and we'll talk about how to estimate the error and stuff like that. That's something that we're going to look at pretty soon here, but you can just zoom in and see how the closer and closer these things get, the better, the more terms you add. And the theorem that we'll see in the next class is when you let n go to infinity, it will approximate it exactly. And so obviously you can't let n go to infinity, but the idea is you can get as close as you want by using more and more terms, is sort of the idea. Let me just see how many zeros I can throw on there. At some point, it becomes like too computationally intensive. Like you can see right now, my computer's working hard trying to calculate 100,000 terms. And Maple, to be perfectly honest with you, isn't the best program for doing this kind of stuff. There are better programs and quicker programs out there, but this is what we're using here. Anyway, that's probably too many. I'm going to quit. I forget how to quit, though. I'm just going to quit there. So down at the bottom is actually how to calculate the error, but we're going to talk about this in a later class. So this is calculating the error that we'll look at in a later class. The Fourier series B is doing the same thing with the other function. And I just heard a question pop up. Let me see what that says. I thought I heard a question pop up. I don't know what that noise was. Is that from here? Someone's asking for help. Okay. Roger that. So anyway, this is the second one. This is the one that doesn't have the correct type of symmetry. And so the difference between this code and the last code is in the last code, I just went ahead and programmed the Fourier series right in there. But in this second code, we're actually calculating the coefficients ourselves, right? So here I am doing the A0 calculation. Here is the AN calculation. And here is the BN calculation. And you can see we get the values that we found. These are the same things we wrote down on that piece of paper. This one looks a little bit different, but they like multiplied by -1 or something weird in there. But it's the same coefficient. And so you can use this code as a base to find other Fourier coefficients, in other words, for homework problems and things like that. Right? You would just have to change the f part of this. You'd have to redefine the function that you're approximating. And again, here I am defining the function in a different way. So in the first one, I had literally just typed in the coefficients, right? In this one, I'm giving you the general form. Like this is just the definition of a Fourier series, right? And then the AN, the A0, and the BN are going to be calculated and come from earlier in the code. And then you can plot the things, right? So here I am plotting the normal function and then our approximations. Let me just plot the normal function, and you can play around with this too if you want. So that's the normal function. And then when we approximate it, what you can do is you can do something like this. All right, I just did F, where you can change. You can change the number of terms being used. So right now I'm using 3 terms, and you can see that it's an okay-ish approximation, but it's not really matching up very well. And then the more terms you add, so now I'll add 10 terms and I'll run it again, it gets a little bit closer. Right? If you added 50 terms, you're going to get a little bit closer. Right? That's pretty damn close right there. Right? If we did 500 terms, it's probably going to look really nice. Right? That's a real nice approximation right there. You can kind of zoom in and see just how close those two things are. This is kind of like the problem in homework 4 number 1, where you are approximating e to the x, right? You get like a nice approximation. But the thing with this is you can approximate periodic functions almost exactly, which have lots and lots of applications. So I think what we'll do in the next class, like I mentioned last time, is start by watching a couple hopefully interesting videos about some of these applications. And so I wanted to let you play around with this a little bit. Maybe you could try figuring out the one we didn't, that I haven't shown you. So the one on page 16, right? The absolute value one, you could try that. So that would involve just redefining the piecewise function a little bit. And it's actually going to be pretty easy to do. It would literally just be changing this, I think. And so maybe take a second to think about how that would work. How would you redefine this function to approximate the one that's on page 16? So maybe just take a minute and think about that, and then we'll do it together. I'll do it, and that'll be it. By the way, you'll have to save the stuff on your own computer, I'm pretty sure, remember. So let me look. I'm going to save this one into my folder. Take a second to think about that. Maybe even try it yourself, and then I'm going to reconvene in just a moment here and do it. We can do it together. All right, I'm going to step away for just a minute here. I will be right back. Give this a try. See if you can approximate the one on page 16. All right, so is this as easy as I'm thinking? Is anyone able to do that? I think all we need to do is just change this and this, right? So the absolute value when it's negative equals minus x, and when it's positive, it equals x. That's what the new periodic extension looks like. And then everything else in here is just generic code. So this is going to recalculate the new coefficient. This will recalculate the second coefficient. This will calculate the third coefficient, right? We get the third one being 0 because it's an even function. And then we can calculate some number of terms. Let me just do a couple terms at first, and then plot them. Wow, even just 5 terms looks pretty good already. See if we can zoom in here a little bit. Yeah, I mean, it's really close, even just with 5 terms, right? Let's even just try 2 terms and see what that looks like. 2 terms is not super great. Oh, already not horrible, though, right? If you did just probably 20 terms, it would look really, really close, I think. And again, we can talk about calculating the error and figuring out just how close they are pretty soon here. So you can see that's really, really close. You're approximating that absolute value function with the Fourier series. And again, you can use this in a lot of the homework questions. Like if I just kind of switch over to the homework real quick, this is the homework that's due. Oops, wrong one. This is the one that's due in a couple classes. You can, no, this is the one that's due Thursday. Next one. This is the one that I'm talking about. You're welcome to use, Maple for a lot of these. There was also a typo in it, by the way, so I re-uploaded this. I don't know if you had already downloaded it from Blackboard, but I saw that there was a typo right here. So anyway, so providing a plot for the first 200 terms, that's going to use Maple. right? Provide a plot. That uses maple. Number 3 is not a maple question. And I don't think number 4 is either. Number 5 can be a maple question. And I think I accidentally put this at the bottom of both of these things, yeah. So anyway, you're welcome to use maple for, it seems like, most of homework 6. And so I would suggest starting with this code or potentially one of the other ones or combining them maybe. And I'm using those. Can I answer some questions? Thoughts about this stuff at all? Just kind of looking ahead, the way that this is used in image compression, or anytime you want to compress something on a computer, a lot of times it uses Fourier series because it represents like audio waves or visual signals as a Fourier series. So rather than storing all the information that's in like an image or a song or something like that, it can represent some of those things with a function, this Fourier function, for example. And that's less, that requires less memory to store than the MP4 itself or something like that. There's obviously a lot more to it, and so I'll see if I can get a nice video. I've got a couple of videos that I think sort of allude to the uses of this stuff without getting too technical, and so that's what we'll start with next time. I'm happy to hang around if people want to chat, if you've got other things you want to talk about, but that's all I've got for today. And so I'll just remind you again that there's more homework due Thursday. I will be grading up. I've graded project 1 if you want to look at your grades. And then I will be grading up homework 4 now that I can sit at my desk again. So I've got hanging around if anyone has questions, but thank you very much. I'm going to stop this video and then post this video online. Thanks, guys.